How do variational autoencoders, VAEs, generate new data? Imagine being able to create new images, text, or sounds that are similar to what you've seen before, but with a twist. That's what variational autoencoders do in the world of artificial intelligence. They are a type of deep learning model used in generative AI, which means they can produce new data that looks like the training data they learned from. But how exactly do they do this? Let's break it down in simple terms. First, think of a variational autoencoder as having two main parts, an encoder and a decoder. The encoder takes your original data, like a picture or a piece of text, and compresses it into a smaller, more manageable form called a latent space. Instead of just copying the data, the encoder turns it into a set of numbers that describe the essential features of the input. Unlike older models that just stored fixed points, VAs encode data as a probability distribution, usually a normal distribution. This means each input is represented by a range of possible values with associated chances, making the process more flexible. Next, during the creation of new data, the model randomly picks points from this probability distribution in the latent space. Think of it like drawing a random card from a deck. These sampled points are then sent to the decoder, which reconstructs the data back into its original form. Because the latent space is continuous and probabilistic, each sample can produce a slightly different output, giving us variations of the original data. This is how VAs generate new images or text that are similar but not identical to what they learned. Training a VAE involves two goals. First, it tries to make the reconstructed data as close as possible to the original input, which is called the reconstruction loss. Second, it makes sure that the distribution in the latent space matches a standard normal distribution, which helps in generating smooth and realistic variations. This balance allows the model to produce new data that looks natural and coherent. In real-world applications, VAs are used to generate realistic images, create new artwork, or even produce synthetic data for testing. For example, they can generate new faces that don't belong to real people or create new styles of art by sampling different points in the latent space. They are similar in spirit to other models like DALL-E or Midjourney, which generate images from learned representations, but VAs focus more on the probabilistic aspect of data generation. From an ethical point of view, the ability of VAs to produce realistic synthetic data raises questions about authenticity and misuse. It's important to use these tools responsibly, being transparent about what is real and what is generated. This helps protect creators and society from potential harm. In summary, VAs generate new data by encoding inputs into a probabilistic latent space, sampling from this space, and decoding those samples back into data. This process allows them to produce new, unique examples that still resemble the original training data. They are a key part of the growing field of generative AI and help push the boundaries of what machines can create.